As I'm sure all of you know, the Hercules Dome Ice Core Project is a new project funded by the U.S. National Science Foundation to drill a core at Hercules Dome, which is shown on the map there. Welcome to this webinar. It's hosted by myself, Eric Steig, and TJ Fudge. And I just want to highlight and mention my collaborators on this project: Murat Aydin, TJ, who I just mentioned, Joe Suni, Heidi Roop, and Mark Twickler. And site selection work, radar, and other related work at Hercules Dome to figure out exactly where to drill is being led by Knut Christensen, along with Nick Holshoe at Amherst, myself and TJ, and a number of UW graduate students who are listed on the slide here. And finally, you're all welcome to and encouraged to attend our workshop, May 10th to 11th. This workshop is intended in part to start talking about collaborations, initially mostly within the US ice coring community, but international collaborations are absolutely encouraged and welcome. And also because it's pretty early in the project, we're not drilling for a few years. There's time to do a lot of other things. And one of the things we're trying to do is broaden the participation in polar science in general. And the workshop in May will include not just ice core people, but also folks that are doing related work, ice sheets, for example, ice dynamics. And we also have a speaker who's an expert in the communication of sea level rise to policymakers and the public. And finally, so if you would like to come to the May workshop, go to herculesdome.org/registration and register for that. And also look for more upcoming events on our website. We'll be organizing a number of additional webinars and such over the coming year. So without further ado, I'd like to introduce our speaker, Eric Wolff. Eric Wolff is a Royal Society research professor in the Department of Earth Sciences at Cambridge University in the UK. He's a chemist by training. He has studied ice cores in the Antarctic and Greenland for the past 40 years. He also continues to carry out research into the chemistry of the lower parts of the Antarctic atmosphere. Until June 2013, he led the ice coring program at the British Antarctic Survey before he moved officially to Cambridge. Nice, easy move across town. One of the really important things that Eric is known for, in addition to his research, is leading the Science Committee of the European Project for Ice Coring in Antarctica, EPICA, which resulted, as I'm sure most of you know, in the 800,000-year records of climate from Dome C. And he also co-founded and co-chaired the International Partnerships in Ice Core Sciences and co-led that for many years with Ed Brooke. And finally, he chairs the Royal Society's Working Party on Climate Change, leading a number of public and policy-facing reports. So Eric has been a really important contributor to Antarctic science, as I said, for a very long time. And it's my great pleasure to introduce him and to thank you, Eric, for giving this webinar in support and collaboration with our project. So I'll turn it over to you if you can share your screen and just let me know if there are any issues.
We'll share my screen. Okay, hopefully that looks okay.
That looks great.
Okay, well, thank you very much. And thank you everyone for turning up. I realize it's all kinds of different times of day when you don't normally have seminars, but happens to be a nice time for me at the end of the day. I'm impressed by how many people want to know about Hercules Dome and want to hear this talk. I'm a little embarrassed in a way to give it, because what Eric asked me to do was a kind of combination of things of talking generally about, enthusing generally about Antarctic ice cores and what's exciting in ice core research at the moment, and also talking about what I would see as a bit of a twin project to Hercules Dome, which is the Skytrain Ice Rise Waxwing project. And the second one's fine, because most of you won't know too much about it. But the first one, I think there's a bunch of people on here who know just as much about ice cores as me in many cases. And I'm going to be picking some things that I find particularly fascinating. And that means I'm probably not picking everyone else's favorites. Indeed, I might not even mention other people's work. So I'm on a bit of a hiding to nothing here. But anyway, let's keep going. So what I said I would do is to do first an overview of why ice cores are such a great thing, just in case there are some people on here who aren't into ice cores at all. And then a couple of recent advances that have excited me. And then I'm going to talk about the last interglacial, and that will lead on to why we need Hercules Dome. So the very simplest, that's an ice core, just in case anyone wonders. And that's where we get them from. I don't need to say any more about that slide at all. So I'm going to talk about 3 ways in which ice cores have changed our perception of the world. And I think this is really a tricky pick, but I think these are the 3 things, if you asked probably even members of the public, but certainly the wider climate and science community, what they value ice cores for, these would probably be them. So the first one is quantifying climate forcings. And the most famous thing, of course, is the greenhouse gases. So if we didn't have this record from ice cores of the last 1,000 years, which is what I plotted on here, then we would still be endlessly arguing with people as to whether what we've seen in CO2 in the last 50 years or so is natural or anthropogenic. We would probably know by now, but we'd still be arguing about it, whereas this makes it completely unequivocal. It's not just CO2, though. I think we should remember ice cores are a crucial part of actually the majority of forcings that go into climate models. The other greenhouse gases, volcanic eruptions, they're a very large part through beryllium-10 of telling us what the solar forcing's been beyond at least the last century. And of course, although it's very regional, they tell us about aerosol, which is critical for understanding the forcing in the other direction from aerosol. So that's my first pick for why ice cores are really important, or have been really important over the last few decades. Second one is the direct observation of the link between climate and the carbon cycle, and that comes from the EPICA project that Eric mentioned, with the 800,000 year record of, I put temperature, it's actually deuterium translated into temperature at the bottom, and CO2 at the top over the last 800,000 years, running from left to right. I think all my slides are running in the correct left to right direction for time, in case anyone needs to orient themselves. I always think when I present this slide to people, well, there are 2 things that are important about it. The one is the rather obvious one that links back to the last one, that if I wanted to plot the last 100 years of CO2 on the same slide, I'd have to go off the top of the page in order to get it on, because it's now over 410 parts per million. And the highest value on there is 300. The second thing is that these 2 plots look incredibly similar. I mean, when you just step back, they look the same. And most of us know where the bodies are buried and know where they're slightly different. At the beginning of the last interglacial, there's one of them in marine isotope stage 11. I should actually be using a pointer, shouldn't I? That would make life a bit easier for everybody. So in marine isotope stage 11 there, it looks a bit different. And here at the beginning of the interglacial, for example, it looks different. So there are places, but nonetheless, for most environmental scientists, if you went out and took, shall we say, a marine sediment core, and then another one 5 meters away from it, and measured the same thing on it, they wouldn't look this similar. And yet these are 2 completely different things, the temperature in Antarctica and the global carbon dioxide record. So they really do show how closely linked CO2 and climate are in a very visual way. And then my third pick is millennial scale climate change, Danskard-Oeschger events, and all the millennial scale stuff that goes with it. Of course, we've known about them for a very long time, but I've used one of the recent papers from Waste Divide that really shows the dynamic of the whole thing. So you've got Greenland temperature at the top with the very rapid jumps in climate. You've got methane underneath, looking very similar to Greenland temperature. And then you've got 2 different versions of Antarctic temperature from Waste Divide and from East Antarctica, showing this kind of, it's not in phase or out of phase, but it's certainly not in phase, but it's also not anti-phase. It's this dx by dt plot that Greenland and Antarctica show with each other, which really tells us about the dynamics of the bipolar seesaw, and almost certainly how the overturning circulation plays out in climate. So those are my three picks. I think ice cores are so powerful, firstly, because they cover so many timescales. We can get really good information in some ice cores on sub-seasonal scales, albeit over shorter timescales, but we can also go so far up to 800,000 years, albeit not at annual scale, and perhaps further. Like most paleoclimate archives, they contain proxies, but they also track real air, and that's a really unique feature. And there are so many things that can be measured in the same core that cover both regional and global parameters, and not just about climate. So that's my selling point for ice cores in general, in case anyone was thinking they didn't want to be in this core at all. So now, what do I find exciting over recent years? I'm going to take just three topics, and that's why inevitably I won't pick the ones that you like, and so you'll be offended. Some of you who were at INCWA 2 years ago will have seen some of these before, so you'll already know roughly what I'm going to say, because I did the same kind of thing. The first one is kind of an unusual pick because I've chosen the x-axis. We normally worry about the y-axis, what we're measuring, but time is incredibly important in ice cores, as we all know. And so I'm going to talk about time for a little bit. So the first thing is that over recent years, we've got incredible new standards of synchronization, firstly in the gas phase, particularly through methane, where we've become used to matching up records from the north and south and from across Antarctica at millennial scales. But it was a revelation to find out that we really could do it at subcentennial scales, as Rachel Rhodes's paper in 2017 showed. So here you've got NEAM at the top and waste divide at the bottom, and you can see every little wiggle translated and lined up there. And the same here with waste divide and Fletcher promontory, which is a very thinned ice core at this stage, and yet still you can do it. We've found that you can do it in the ice phase as well through the volcanic records. I don't think I ever thought we'd get to the stage where we do it convincingly between Greenland and Antarctica, but Anders Svensson's paper has done it. It's is it convincing? Well, that's for you to judge, but it's semi-convincing. It's convincing enough that I think we think it's a good job. I think you probably need the methane record to home you in on the right part of the core before you start matching up the volcanoes. I'm not sure you can do it in a kind of floating bit somewhere in the middle very successfully, but some others may comment on that later. But anyway, it means we can now link up Antarctic cores, which are the kind of ones from the orange down, and Greenland cores, which are these three at the top, and we can link them up effectively to the year in the ice phase. So that's great, but I think even more exciting to me is that I now think we're managing to synchronize different paleo records at a global scale, which we need to do if we're going to give proper targets for modelers as to what happened when we go across, say, a Danskard-Oeschger event. And the reason why we need to improve what we're doing is because our age scales in many cases are very nice, but are stated as being very imprecise. And I give the example of GICC05, where the stated uncertainty by the time you get to Greenland interstadial 8 is absolutely huge. It's large enough that you don't really know which Danskard-Oeschger event you're in. And we all know that's not correct, but we don't know how to turn it into a smaller number. But I think there have been at least 4 breakthrough studies in the last few years that will allow us to do this, as long as we're willing to take the step. And to some extent, that step has been taken in the waste divide age model. So the first of those is linking Greenland to the tropics through linking the Greenland temperature with methane. This was done by Julia Rosen over the Bolling onset, using the temperature signal that's in nitrogen 15, so also in the air bubbles with the methane record. So that enables you to align things that are in the same record, and getting around this problem we have in ice cores, that the age of the air is not the same as the age of the ice. And she concluded that the tropics couldn't lag Greenland by many decades, at least at this climate change. So that's a Greenland tropical link for at least one event. Then we've got the Greenland Antarctic link that was achieved by this very clever paper by Christo, I don't know if he's on the call, Christo Bizet, where by linking all the Antarctic cores, he was able to create a principal component analysis of Antarctic climate over this period of 60,000 years, in which he found what he described, or what they described, as an oceanic component and an atmospheric component, which is the second component. And that atmospheric component can then be lined up through the methane with Greenland. And they concluded that the atmospheric component in Antarctica lagged the climate, the Danskard-Oeschger signal in Greenland by 28 plus or minus 40 years. In other words, it's in phase to within certainly less than a century. So that's Greenland, Antarctica. And then there's Greenland to speleothem records. This was done by Florian Adolfi in 2018 using the beryllium 10 record and matching it up to carbon 14 in tree rings and in speleothems. So all cosmogenic things that therefore should show the same signal. And you can kind of see they do. It's a bit of a messy diagram, but you can see it. The beryllium 10 in the ice is the gray, and everything, all the other data are the different speleothems and tree ring records. So you can see how that can be lined up to within a few decades. And using that, they concluded that the onset of Danskard-Oeschger warming is going back to 40,000 years is within the uncertainty for Greenland and the speleothems. So the onset of a DO event in speleothems in Europe and China was at the same time as that in Greenland. And then finally, a paper that I was involved in recently is speleothem to speleothem, which was using compiling a whole bunch of speleothems from China, Europe, and South American monsoon regions. And I won't go into the details because I just don't have time. But the conclusion was that where you could compare the regions, where you had enough data to compare the regions, then the onset of the DO event that you saw in Europe, China, and South America, where it's a different signal, it's a negative signal effectively, but the onset was again at exactly the same time to within the uncertainty of the dating, certainly less than a century. So what we have, putting all those things together, is a kind of, I know it looks like a coat hanger, but it's not meant to, it's meant to look like a linkage. We have the onset of what we recognize as the DO event. We have the linkage between Antarctica, Greenland, and all the three speleothem regions, suggesting that to within a century, the onsets of those DO events are synchronous. And that, I think, gives us the green light to use speleothem dates, which are very precise in absolute terms, to tie down our ice core dates, which have very nice counting records, but in absolute terms have very large uncertainties. And I think that's something we've all been scared to do because it's assuming something that we should be testing, but I think it's now been tested and I think we can assume it. Of course, we can't go down to that last decade still, but I think that's important stuff that will really help us. And of course, we can also use it on older material. If you go back to say 400,000 years and the beginning of marine ice stage 11, the speleothem records also show what look like Danskard-Oeschger onsets, and they're dated to within better than 1,000 years. So that would certainly allow us to improve, for instance, the Epica dating uncertainty, which is currently 6,000 years at that age. Okay, that was all about dating. Now I want to talk about new proxies, and just to give you a context, because I'm going to say something about volcanic material, just to remind you that we've got these fabulous records of volcanic forcing from Greenland and Antarctica tied together from Michael Siegel's paper and more recent papers. I actually saw today that a new paper giving a volcanic record for Antarctica covering 11,000 years appeared in JGR from Yi Hong Kong. So we've actually extended it in a paper that's in review at the moment to says my internet connection's unstable, but hopefully you can still hear me. So we've actually extended it to 200. Get really excited about October. They'll tell you that it's the largest eruption in the late Quaternary. And why don't we see it in ice cores, or why don't we know which one it is? And the fact is, Toba appears roughly where that arrow is there. And it clearly isn't the biggest record in the ice core, the biggest signal in the ice core record, but nonetheless, we'd still like to know which one it is. So the way to get at, or one way to get at that is to look at, so the candidate peaks were identified by Anders Svensson's paper a few years ago, and there are 7 or 8 candidate peaks that could be Toba in about the right age range. So what's been looked at more recently by some colleagues we're working with in the University of St Andrews is mass independent fractionation, which means you get a different signal for 33S from what you get for 34S, essentially. And mass independent fractionation implies that the material, that the sulfur dioxide has been in the stratosphere before it became sulfate. And there's also evidence that there's a positive correlation between the magnitude of the mass independent fractionation recorded in ice cores and how high the eruption went. So a sort of working hypothesis is that if Toba was such a big eruption, it should show a particularly large mass independent fractionation. So here are the data. It's a little bit messy. It's in climate of the past discussion, so it's in review. It's a discussion paper still, so you can comment on it if you wish. These are 3 of the candidate eruptions, and I'm just pointing at this one in particular, where there's a mass independent fractionation of 4 per mil, which is huge, much larger than anything that's been seen in more recent eruptions like Tambora or Samalas. So that looks like it could be the candidate for being Toba. I don't think it's definitive or proved yet, but that's the kind of new proxy that people are developing in ice cores. The other one I wanted to talk about was mean ocean temperature, and I imagine there are some people on the call today who've actually developed this method, so I'm really preaching to the choir here. But I think this is a fantastic new proxy, really impressive. It arises because the solubility of noble gases in seawater depends on temperature, and so when you change the ocean temperature, you change the amount of, say, xenon or krypton in the ocean, and therefore you change the amount in the atmosphere because there's a fixed reservoir. So you can measure this in ice cores, and it really should measure the mean ocean temperature, which is quite phenomenal because that's something that's extremely hard to measure today. It is something that's produced in models, so it's very useful. And there's a whole bunch of papers that show this. I just want to talk, because it's going to come back later, about the last interglacial. And this is Sarah Shackleton's paper from last year. And it shows that the mean ocean temperature, which was about 2 degrees below present in the glacial stage 6 for the last interglacial. And for most of the last interglacial, it was actually at around 0, meaning about the same as in the Holocene. And you can also see that in the plot on the right here. But at the early interglacial, it was about 1 degree warmer. So that aligns with the fact that Antarctica was also considerably warmer than today at the beginning of the last interglacial, around 128,000 years ago. So that's a really interesting event. It's telling you something about well, it's telling you about ocean heat, but it's also telling you about something about the planetary energy balance. So that's new proxies. And then the third thing I wanted to talk about is new ages, going back beyond 800,000 years. Many of you will know that from marine records, we know that climate, which has been varying on a timescale of roughly 100,000 years over the last 800,000 years, varied on timescales much closer to 40,000 years, which is the obliquity cycle, the tilt of the Earth's axis, back before 1 million years ago. And we really want to get an ice core record that goes back into that period, not least because it would tell us what the CO2 did, which would rule out or rule in one of the possible mechanisms for this change from 40,000 to 100,000 year cycles. And I would argue actually that this is fundamental science on a par with discovering some new particle or discovering a new astrophysical phenomenon, because if we don't understand this, we don't really understand why we live in a 100,000 year world. And so we don't really understand why we live in the mild conditions of an interglacial today. So there are several international teams aspiring to drill an older ice core. Probably I don't think anyone will be offended if I say that I think that the European, Australian and Japanese teams are probably closer than other teams. But there's also an effort to obtain old ice from blue ice at Allen Hills, and some data have been published, some snapshots. I'll concentrate for obvious reasons on the European project, just to say, for those of you who didn't go to any of our other briefings about this recently, that the European project called Beyond Epica has chosen its site at a place called Little Dome Sea, which is here. It's about 2,700 meters deep. It looks as though it's frozen at the bed and always been frozen at the bed. And modeling suggests that we will get 1.5 million year old ice well above the bed. But of course, that's yet to be discovered. That's what it looked like. Some of you already saw it in Carlo Barbanti's background earlier. That's what Little Dome Sea looked like in January. The project's officially started. The drill tent's up, as you can see there. The drilling starts in the Fern in the next field season, and the old ice should reach Europe in summer 2025. So that's something to look forward to. Okay, so now finally, but quite a long finally, to get on to the Waxwayne project, which is probably the closest cousin to Hercules Dome and what I wanted to spend the rest of this talk talking about. So Waxwayne stands for Warm Climate Stability of the Antarctic Ice Sheet in the Last Interglacial. Okay, sorry, I'm just moving something out of the way on my screen. I'm sure you all guessed that from the acronym. The truth is that I can never remember what the acronym stands for either. It's funded by the European Research Council, and I'm contractually obliged to make sure that you know that. So that should have reminded you. And it's led by Cambridge and the British Antarctic Survey. And you can see some of the names there of the people who are involved, and I'll come back to those. Now, so these are the Waxwayne team. Currently, it doesn't actually include everyone who's working on Waxwayne ice, but includes all the people who've been funded by Waxwayne at least. And I wanted to put their pictures up because I think some of them will be, some of them are on the call, some of them will be very interested in Hercules Dome, and who knows, some of them might even be looking for postdocs in a few years' time, for further postdoc positions in a few years' time. Just to tell you, now I'm going to mess this up by forgetting to say something about somebody. So Christos working particularly on total air content of the ice. Helena's working on a laser ablation ICP-MS analysis, as well as the chemistry of the ice. Mackenzie's working on the chemistry of the ice and the continuous flow analysis. Isabel's actually, excuse me, working mainly on synchronizing records from around Antarctica and on the new Sherman Island ice core, which I'll mention. Santia is doing isotope modeling that will support the project, and Rob Mulvaney, of course, is doing everything, including drilling the ice core. So what's the idea of the ice core? And also, I think one of the key ideas behind Hercules Dome, although not the only one. So we have to think about West Antarctic ice sheet and the last interglacial. So we all know the future stability of the West Antarctic ice sheet is uncertain, and it's really crucial for future sea level, for what we're committing ourselves to in the next century and centuries. And models can go so far, but really we need some data constraints on what happened to the West Antarctic ice sheet in the past in order to constrain what's going to happen in the future. And a very nice paper came out recently that kind of illustrates that. If they ran an ensemble of models, I think it's all PISM modeling, and they ran an ensemble, and they found that basically if we could show that in the last interglacial West Antarctic ice sheet disintegrated by less than 3 meters of sea level equivalent, then even under RCP 8.5, we'd only get a few centimeters of ice from West Antarctica, sea level rise from West Antarctica in the next century. But if it mainly disintegrated in the last interglacial, then we could get a meter in the next century, and of course much more beyond that. So knowing about West Antarctic ice sheet in the last interglacial, which is the only time really that we can go back to look at what happened with a smaller West Antarctic ice sheet, will offer a strong constraint on its future behavior. So the last interglacial is, for those who don't know, it's a period about 130 to 115,000 years ago, when both Greenland and Antarctica were warmer than present, and at about the levels that we expect in 2100 under some scenarios. So that's a very vague statement, but it's qualitatively correct. The reason for the warmth, of course, was nothing to do with CO2. CO2 was actually about at pre-industrial levels. It was to do with changes in Earth's orbit and ocean circulation. But it doesn't matter for us. For us, it means that the polar regions were warmer and therefore do provide something of that bad word analog for the future. And we also know that sea level was higher than today. The sea level scientists have converged on a value of about, over the years, on a value of about 6 to 9 meters above today. And you can probably only get a couple of meters from Greenland, and you can definitely only get 1 meter from thermal expansion and mountain glaciers. So you've got to, it feels as though you need something from Antarctica. And West Antarctica, of course, is normally fingered for that. So the question is the West Antarctic ice sheet doomed? So there's recent ice sheet, well, it's not recent anymore, but it was when I first used this kind of slide. So Rob DeConto and Dave Pollard's 2016 paper, which they followed up with more detailed work recently, suggests that the West Antarctic ice sheet would have been lost in the last interglacial. Eric showed the same plot, I think, this same map in his introductory slide with Hercules Dome on the edge of the ice here somewhere. And they showed, among other things, which is relevant for the SkyTrain project, they showed rapid retreat of the Ronnie ice shelf due partly to the ice cliff collapse as a precursor, actually, in their model, I believe, to the rest of the ice sheet retreating. And I would say that it's somewhat to our shame as paleoscientists and ice core scientists that we actually have no hard evidence either way about whether waste was actually lost in the last interglacial. I mean, the math says something must have happened to Antarctica just in order to close the sea level budget, but actually we don't really have anything convincing in either direction. So the question is, did waste disappear in the last interglacial, or perhaps more subtly, when and by how much did it retreat? So we started the Waxbrain project. It started in 2017, but the first year was just preparing for the field season. And our solution is to drill an ice core in a dome around the West Antarctic ice sheet. So this is much the same as one of the justifications for Hercules Dome. Drill an ice core in a dome around waste at a place that we're pretty sure survived the interglacial, but that's sensitive to what happened in the West Antarctic ice sheet. And of course, and I'm glad I put this sentence in because I saw some people in who would certainly want me to say this would be complemented by, or would complement, other ways of getting at the same question: cosmogenic measurements from rock underneath the ice, telling us when the ice that's above sea level was last exposed to the atmosphere, and therefore there wasn't ice on it, and marine cores that might tell us something about what was happening on the margins, although that's tricky because of the last glacial maximum destroying much of the evidence. So I see this as a very complementary set of studies where we need to drill ice cores and also look at the cosmogenic and marine data in order to come up with a comprehensive answer. And I certainly hope that in Hercules Dome, there'll be space for these people from these complementary disciplines to join in some of the meetings. So a caveat of what I'm going to say is that we don't have all the results yet, so I'm not going to answer the question that I've asked today. So I really think that, and I conceived of this actually as part of the international strategy, because I knew even when we were starting to think about it that people wanted to drill at Hercules Dome. I think that the ideal thing would be if we could drill at places all around West Antarctic ice sheet in a kind of quadrilateral, because I think that would be the most interesting for looking at a signature, particularly in the climate signals, in the isotope signals, to look at a signature of West Antarctic ice sheet having been removed. Whereas there's always a danger with one core that we get a particular answer, but it's for the wrong reason. So I think we need a network of cores. Mount Moulton there is a blue ice horizontal core for which there is already data. You can go back to paper by Korotkic in, is it 2013? I can't now remember. So there is already some data from there. We actually drilled as well at Sherman Island as part of our project, but I should tell you now, with rapid access drilling, to see whether it did have old ice, I should say that we didn't reach the bed, so we definitely don't have old ice there. We have a very nice record for the recent past probably coming up, but we didn't reach the bed. But I think SkyTrain in combination with Hercules Dome will be great. And this is just another version of what happens if you lose West Antarctica. This comes from a Nick Gollidge paper. It's not actually a last interglacial simulation. It's a high temperature simulation. And you can see that there is still ice there on SkyTrain ice fries, which is encouraging. So why did we choose SkyTrain ice fries? So the first thing is that the models have it surviving even when West Antarctic ice sheet disappears. The second one, which I think makes it very attractive, is that it's obviously going to be sensitive to waste. It's right next door to it. So it's clearly going to be sensitive to it. And it's also going to be very sensitive to what happened to the Ronnie ice shelf, which you remember retreats rapidly in DeConto and Pollard. It's right next to the Ronnie ice shelf. It's protected by the Ellsworth Mountains from being overridden by the inland ice, so there's not any serious danger that in the last glacial maximum the inland ice overrode it and stopped it being a dome and therefore changed the flow pattern. It's got excellent radar layering, as you can see, with a very nice Raymond arch, and Carlos Martin estimated for us that we would get last interglacial about 30 meters above the bed, which turned out to be quite a good bet. We drilled through the top of the Raymond arch as it appears at depth, so that's where the drilling occurred. I'm still not quite sure whether that was a good idea or not. It was a good idea because it took the interglacial further from the bed. You'll see there are some concerns about the record deeper down that maybe wouldn't have been such a concern if we hadn't been on the arch, who knows. So the core was successfully obtained. It's 651 meters deep. The 10-meter temperature is -26 and the basal temperature -15, so it's definitely cold. The accumulation rate a bit lower than we thought, about 15 centimeters water equivalent a year, which is a bit lower than we were expecting it to be. Of course, that's good. That means the interglacial is higher up than we would have had otherwise. I just need to give you a little bit of flavor just because it's fun and you need some light relief. We all need it. I need to give you a flavor of the field season. It was drilled in one field season. The material had been taken to the site, or the heavy material like the drilling fluid had been taken to the site the previous season by the Bass Traverse, the same one that's supporting the Thwaites project. We had 6 to 8 people on site during the season. I think many of you are probably aware that the UK operation tends to do things in a slightly, what's the correct word for it? It's not spare, I think is the word, a slightly spare fashion with rather limited facilities. So we had 6 to 8 people on site, about 6 weeks of drilling. We produced 136 boxes of core that were flown out in the Twin Otter down here. This picture here was Christmas, if you're wondering why we're standing next to a wooden tree. And you can look back at how the field season was on Twitter and on our blogs. There are some more pictures of it, of the campsite and the aircraft. The parallax question of how you get that many ice cores into that aircraft. And then this is my favorite picture because this is actually the last core, and in there you can see a pebble that told us that we were near the bed. So that's why this very boring looking picture is there. I think I've got a bit of video, which I think I've got time to show here, of drilling. Sorry about if you can hear the music, I'm sorry about that. That's the driller's prerogative. Just wanted to show you a bit of drilling for those who haven't been in the field. This is the drill tent, of course. The drill being tilted to the vertical. It's essentially a copy of a Hans Tausen type drill, which is exactly the same as you'll be using at Hercules Dome, where the 403,000 is also a copy of a Hans Tausen drill. Okay, we'll cut them off. Won't make you watch any more of it. So what are we actually hoping to get from the ice core? Well, I think there are 4 key indicators we're going to look at. The first one relates to the Ronny ice shelf, which I think we're particularly suitable for. Our site is currently 600 kilometers from the edge of the ice shelf, and therefore from any source of sea salt or marine biogenic material, so sea ice or open water. So if the Ronny ice shelf retreated, then SkyTrain would be 50 kilometers from the ocean. It would be a seaside resort. And we'd easily see that in concentrations, increased concentrations of marine ions. There have been surveys going across the Ronny ice shelf, and if you get to 50 kilometers away, you should get concentrations of sea salt that are several times, a factor 5 times higher than when it's 600 kilometers away. Then the second thing is looking at the geographical pattern of climate, and this is where I think this pattern of having several cores will come in. It'll be very different if waste is absent than if it's present. So in order to interpret those isotope measurements, we're going to need modeling results. There have already been some from Eric Steig's paper in 2015, from what Max Holloway and Santiago Grosso have done in the UK. And we've got some more experiments running at the moment with what we call a DeConto and Pollard ice sheet and with what we call a Gollage ice sheet. So hopefully we'll have some more ideas of what we might get. And then there are other things we can look at. If West Antarctic ice sheet is lost, then the elevation of SkyTrain would change because of a slow rebound. By measuring the total air content, we hope to estimate the past elevation. We're fully aware of how difficult getting past elevation from total air content is, and that's why there's a postdoc dedicated to that. And there are other things we can look at, which I won't talk about. Analyses have been underway. Of course, they've taken longer than they should have done because we haven't been able to get into the lab at all times. We've essentially run one CFA strip through the melter with a whole bunch of things. The diagram at the bottom you're not meant to read, you're just meant to think, wow, that's a complicated CFA. Using that, we've measured water isotopes, major chemistry, dust, and methane. And then we've done some discrete analyses. Some are still ongoing, but we've done some discrete analyses to support those, which you'll see in a minute. Again, I think I've got a video put together by Isabel Rowell for us, of which should excite some of you who enjoy your time at the ice core facility doing analyses. So here's a CFA strip being prepared. Obviously not quite at the speed. And it's melting. Wow, we melt it fast. And it gets sucked into the instrument in the clean lab, or in the other lab, rather. The debubbler. The waste and some data. Okay, let's move on. So Now on some data, and a caution here, because everything from here on is unpublished and preliminary, so I'd really be grateful if you didn't tweet. You, by all means, tweet and say you're excited by it, but preferably don't tweet and say we saw 100 parts per billion sodium at 10,000 years or something like that. So the first question is, did we reach the last interglacial? So our key way of testing that is to date it by matching up the methane record that we got from the CFA. So this is the methane record that we've matched up from, well, tentatively 180,000 years ago to the present. So firstly, what you can see, I'll just run you through it. The SkyTrain data are in pink, and the WACE and Epicodone sea records are in the shades of blue. So first you can see we've got a beautiful match across here, so that's not a problem. Then we did hit some problems. Running methane on the melter is not straightforward, especially when you've got cracks in the ice, and we had quite a lot of cracks around 3 to 550 meters particularly. We had a particular problem here that we recognized the day after of a leak. And so we had some discrete measurements measured in Bern across that part, and you can see here now that pulls that down and confirms that what looks ludicrous methane numbers really belong down here and do match up across here. We also had quite a lot of spikes that we've had to remove, which were from other, which were from cracks where modern air gets into the methane instrument. We also checked the methane data over in the last interglacial with some discrete measurements, and they look about right. And so we're very, because you can see us following here, we've got a slight mismatch here where we haven't actually lined it up correctly, but it matches up here, and then we go into the last interglacial. So my conclusion is that we did reach the last interglacial, but there's a but. And the but is that we do have some issues. The first issue concerns the last interglacial. It's very obvious that we didn't get what we sometimes call the overshoot here. I mean, maybe it's hiding in there somewhere and we just didn't quite see it, but if so, it must be very thin. So we don't ever reach the highest methane values, which implies that we're missing some ice older than 126,000 years old, even though we very clearly have some ice older than that. So we've clearly lost some ice there. And we've also got some signs that the ice is folded on the old side of the last interglacial. This is actually the one figure that's back to front. So this is the old side of the interglacial, and you can see a reversal here in the isotopes. So we've clearly got some folding on the old side. I guess what we've got is some very warm, or warm when it was laid down, i.e. very viscous, very warm, meaning that it's got the crystal structure and the chemistry of warm ice next to some ice that's the coldest in the record. In other words, it's got the most glacial-like chemistry and crystal structure. And I guess that has imposed some folding, which we're going to have to unfold in much the same way as Neem did. We've got some 18.0 atmosphere measurements being done kindly for us in LSC at the moment, which I think will help us to know exactly where we are. But having said that, I am pretty sure from the values we've got that we did get back to at least 125,000 years and probably 127,000 years. The A scale is still being developed, but once you've done that methane matching, then you can also match up, for instance, the terrestrial lines. So I think we've done a good job here. This is EDC calcium in grey, and this is non-sea salt magnesium in blue and aluminium in the orange colors. Aluminium wasn't terribly easy on the ICP-MS, but at the low concentrations, but nonetheless you can see the match across here. So I think we're going to get a very good match on the dating that's going to allow us to put a good A scale on here until we get to that difficult bit. If you look at the isotope record over this time period, and again, I would discount everything before here. I'm not quite sure where we are, but we're somewhere not quite where we think. The isotope record shows all the features that you get in all the East Antarctic records here, the AIM vents here, back to the interglacial. But it's obviously got much more amplitude compared to those. And that's, I would imagine, showing us changes in altitude at SkyTrain, which is why we recently published a paper about the lapse rate effect on isotopes. We have a story, we think, an interesting story from the early Holocene. When you look here, we're going forward in time from 12,000 years. Here's the isotopes. We've got oxygen and deuterium on here. We've got calcium not doing very much. And then we've got sea salt ions. We've got chloride, magnesium, and sodium. And what you see is that we've got a rise, quite a sharp rise in isotopes at around 8,500 years ago. There, which I would actually interpret as Skytrain ice rise losing elevation. This is at about the time that other locations where cosmogenic dating has been done seem to be losing a lot of elevation. I'm not sure that the timing is exactly the same, but it's certainly a consistent kind of idea that there was quite a large loss of elevation at this time. And then, interestingly, about 1,000 years later, we've got a big increase in sea salt, and that's not an artifact because that shows up in the sodium measured by ICP-MS and the sodium and chloride measured by the fast ion chromatography, so completely independent measurements. My initial interpretation of that is what I showed you earlier, that that could be the Ronny ice shelf retreating and therefore the source of the sea salt getting nearer. So what I'm thinking is that the ice all around the Ronny ice shelf lost elevation at that point, which means that the first point, which means that less ice is flowing into the Ronny, and at some point it retreated. So that's a possible story. It's very tentative, so please don't quote me on it yet. And it's much too early for a last interglacial story, but I will just give you a tantalizing look at the isotopes and the sodium record for the last interglacial. And the sodium is low during most of the last interglacial, but does rise at the end of it. So I don't know whether that's telling us something about maybe when the Ronny ice shelf retreated. And I'm not sure how to interpret the isotopes yet because we don't have the isotope modeling to interpret it. So that's about as far as we've got at the moment. Because I'm on Zoom, as we all are, and I can't, everyone's got their cameras turned off. I don't really know if anyone else is still there and has been listening, but I'll go, oh, thank you, Eric. But I'll just go into my conclusions. So my conclusions for the last, and I'm not going to conclude on the earlier stuff about what excites me, but my conclusions on the last interglacial are firstly that cores reaching the last interglacial on the periphery of the West Antarctic ice sheet should be very informative, not only about the West Antarctic ice sheet, but also about the ice shelves themselves. And I just think they're imperative. In fact, I was anticipating a question about this and I've decided to give the answer even if it's not asked. Some of you, I think Mark in particular, will remember that for years before Waste Divide was drilled, I was being asked by Julie Pallet and others what I thought about it as a project. And my answer would always be, we're all waiting for you to do it. What are you waiting for? And that's my answer about Hercules Dome as well. It needs to be done. What are you waiting for? Get on with it. So the Skytrain core is even better if we can have a Hercules Dome, or Hercules Dome will be even better if it can also look at Skytrain. Skytrain has the last interglacial, but we clearly don't have all of it. So it would be great and completely unique if Hercules Dome does capture that early last interglacial optimum. I have a slight concern that it seems as though the beginning of the interglacial in both Greenland and Antarctica is something that's extremely hard to capture for some reason. So I hope you're luckier than we are. And between us and adding in cosmogenic and marine data, we should be able to put a new constraint on that three-legged stool that has to be level of sea level, the Greenland ice sheet and the West Antarctic ice sheet. Somehow they've got to add up so that the last two add up to the first one. And at the moment, it's a hard struggle to make that work. So I think that's more than enough from me, and I'll stop sharing my screen.
Eric, thank you so much. As usual, I think you did a masterful job of capturing the excitement of ice coring, highlighting some of the recent and older results that make this field so important, and giving us some tantalizing new results as well. Just absolutely fantastic. And I know I speak for everyone involved that we look forward to collaborating with you, especially as the Hercules Dome project gets going and is successful.